to the fourth Mini Science 2018 lecture in our series entitled Women in Science at McGill. And as you all know, this series is made possible through the generous support of Dr. Lauren Trottier. McGill University is located on land which has long served as a site of meeting and exchange amongst Indigenous peoples, including the Haudenosaunee and the Anishinaabe nations. McGill honors, recognizes, and respects these nations as the traditional stewards of the lands and waters on which we meet today. The housekeeping notes for tonight are very good. The water problem has been solved. Last week, the entire building had no water, no toilets were operational. We had to go a long way to get you your water last week. Apparently, that's all been fixed in 1 week. You know that we hold off on our Q&A until the very end, and the question and answer period will be done using this mic. Our volunteers will move around, and you will speak into, even though you don't hear a thing, it's recorded and it will be used for our webcasting. John, the technician from McGill Communications, will be preparing those for us. They will be ready at the end of this series, probably in May, early May. Please turn off any devices that might disturb the speaker. There might be a brief interruption from the intercom in this room. That's happened last week, and we all thought it was some sort of emergency thing. It's central intercom telling everybody in the library that the reference desk, the checkout desk, is closing. That happens around 7. We just ignored it. The speaker just kept moving through her presentation, and we'll do that tonight if that happens. Please don't forget to go online for background readings that are available as links through the Mini Science website. All the speakers in this series have provided us with introductions to their work as scientists, and these background readings accent and enhance aspects of what you hear at the presentations. Special thanks again to the staff from Rare Books. Tonight it's Jennifer Garland along with Marianne. They're attending to their work out there in the reading room. The reading room is not just open for us, and it's not by special appointment only. This Rare Book area is open every day, Monday to Friday, 10 till 6, for anyone to access. You can, once you get in, you can look around, but if you want to find something specific, you don't have to make an appointment. There's always someone at the desk, and you can ask to find whatever it is you have a burning desire to see in Rare Books. Very special collection. Our moderator tonight is Olivia Denson, a full professor from the same department as our speaker. That department, Earth and Planetary Sciences. The speaker brought along a big blue bag full of more things from that department for us to take home with us. What's not taken home, we'll send back with the speaker so they can distribute it even further afield. Don't forget to grab those things tonight on your way out. Olivia has been active as a teacher at McGill since 1973, but she began not at Earth and Planetary Sciences. She began in the Department of Mining and Metallurgy. She's a geophysicist, is her earliest training, and then she moved over to, I guess, was it Earth and Planetary Sciences at that time? Geology. It was still geology, yeah. She has held positions at NATO as a senior guest scientist, at the École et Observatoire de Physique du Globe in Strasbourg, and as a visiting professor with the Department of Geophysics and Astronomy at the University of British Columbia. She worked for various academic postdoctoral and research positions in the early 1960s and 1970s, and in industry as a consultant in petroleum and geotechnology. I encourage you to learn more about Olivia by going to her very informative and fascinating website. I think it's called Sappho? EPS, Sappho EPS. Olivia will now introduce our speaker. That's for you, Olivia, and John says I'm supposed to stand. He said yes, he put in a special spotlight for us.
Okay. This microphone doesn't connect to the audio-visual, or to the audio system here apart. It's all good? Yeah. It is for the recording. And so I have to speak loudly enough so people at the back can hear. Natalya, we've watched Natalya in our department for many years, more years than she knows. We chose to try to get Natalya, to hire Natalya before she finished her PhD. She did her undergraduate work at the University of Toronto, then went to Harvard and did a PhD there. And we hired her as soon as we could catch her. So we've done this with other people, and we get very good people this way in our department. She went on then, we were open to her doing a postdoc, and so we waited another 2 years after her PhD for her to do a postdoc at the Courant Institute, a very famous mathematics institute in New York City. And then she came to us, and now she is the youngest of all the professors in my department, where I'm the oldest. So, and there are many, many years between us. Natalya's work has been rather important in our department in that it has attracted a lot of interest from students. She has a large working group. One of her students is here, Holly. Holly has been a TA in one of my courses. Holly is just the kind of wonderful people that Natalya seems to attract. She has a big group now. What Natalya does is, well, she pays attention to the reality of ice melting, how that affects the Earth, the body of the Earth itself, how that water from the melting ice enters the ocean, changes sea level, and actually deforms the Earth. The ocean basins, when they're loaded with water, are deformed. They take up more water than you might imagine. And so there's a great deal of argument about just what sea level might be at all the coastlines, along all the coastlines of the Earth. This is the kind of story that Natalya can tell us. And her work, she's been working particularly with Holly here. Holly has been working on Hudson's Bay. Hudson's Bay is rising still. The coastlines of Hudson's Bay are rising at about 1.5 centimeters a year. You might get another number from Natalya. But so everywhere on the Earth, as you fill the oceans with water, it isn't necessary that the water runs up on the ocean. And I think you'll come out of this learning something about sea level, learning something about a geophysical story called isostasy, and about climate change, the effects of climate change on the seas. It'll be a wonderful talk, I'm quite sure, because I learn a lot from Natalya. I'm supposed to know what she basically knows, but I had missed some major pieces of my understanding of isostasy, and Natalya has focused me on that. Anyway, she's going to discuss her research. It's a wonderful story. Do pay attention to what you carry away. There will be questions at the end. You'll use this microphone. And Natalya, you pick up the story.
Okay, thanks for having me. This is a great opportunity. So I just wanted to comment, it took maybe a little bit more time than I should have spent trying to position these titles so that they don't cover any person's face on this slide entirely. And I'll talk about where this comes from, but these are just all women who work in Antarctica. And you can look them up on Wikipedia, every one of them. So this, I'm going to sort of start by talking about what I'm going to talk about. So this talk, the title, sort of Earth and Climate Science and Women, is a big category, right? That's a big, broad topic. And so I thought I would say what I'm going to say and what I'm maybe not going to say. So who am I? I'm a scientist. I'm an assistant professor at McGill. I'm a woman, and I'm many other things as well. And so I'm an expert in sea level change and ice sheets and teaching and things like that. But what I'm not is sort of a representative and expert on the experiences of all women in science. And so what I'm going to give you is my take on, great women I've encountered in my career, how I got to where I am, and a little bit about my research and the research of other professors in our department. So it'll be sort of a broad talk that covers many different aspects of me and my work and the people around me. So first, let's just orient ourselves. This is the Earth. Good. This is very roughly the McGill Earth and Planetary Sciences Department. And so I just wanted to start by saying, we're an Earth and Planetary Sciences Department, and many of the faculty, including myself, do think about other planets in our own solar system and exoplanets in other solar systems. But for now, we're going to focus on the Earth. That's sort of broad enough, I think, for today. So, so what do we do? What do Earth scientists actually do? Well, we apply sort of a broad range of principles from other areas, such as physics and chemistry, math, biology, in order to better understand the Earth system. So the Earth system, we have an atmosphere, air around. We have water on the Earth's surface. We have ice on the Earth's surface. There's a solid planet, and there's a whole interior to that solid planet that's very dynamic. And then, of course, we have the biosphere, the life on the planet. And all of these systems interact, and we call this whole thing the Earth system. And so we are a broad discipline that draws on other fields. And we also use a broad range of techniques and tools. So what I do is not necessarily very similar to how someone else in my field might spend their time. So we work in labs with lab equipment, looking at, say, rock samples. We go out into the field and do field geology, so looking at the broad landscape of things. We use data from satellites orbiting the Earth to study the Earth's surface. We might go out into a vessel and explore the oceans, and we use data collected from the Earth's surface around to sort of study the Earth's interior. And so it's a broad range of things that one can do. So, and we do all of these aspects. People in our department work on all of these different things. And so what I'm going to do next is talk a little bit about the kind of research and the women who do it in the Earth and Planetary Sciences Department here. And so I've sort of focused on the faculty, but I just wanted to start by saying that there are many women who are students, postdocs, research associates within our department who all do great work. And I don't have time today to cover all of their work, but they are there as well. So to start out, actually, I'm going to talk about the very first woman who was a professor in our department, is Gabrielle Doucet. And so she was a professor of crystallography at McGill, and actually a nice connection. So she published many papers, and she mentored many scientists, including actually Suzanne Fortier, who is our current principal and vice chancellor at McGill. So she gave the first talk of this session, so it's a nice turnaround to that. And so she did her PhD within our department in crystallography, working with Gabrielle Doucet. And then, of course, we've had an introduction to Olivia Denson as well, but she was another one of the earliest members, women in our department. And she works on sort of broad-scale global geophysics, trying to understand the Earth as a whole, the way that it interacts, the way that it rotates, what's going on with its inner core, how a sort of broad-scale planetary science applying physics. And she's not the only geophysicist in our department, so I'm actually a geophysicist as well, but we also have a seismologist and geophysicist, Jing Lu. So she uses sort of principles of physics and data using seismometers and using GPS to study earthquakes and use the sort of signals that are produced from earthquakes to actually understand something about the Earth's interior as well. And then also can say something about the sort of impacts of earthquakes on us humans and the land. Okay. We also have a number of field geologists in our department. So Christy Row is a field geologist, so she would go out into the field and look at the rocks and understand something from them. And her research is specializing in sort of faults and the earthquake cycle. So faults sort of are preserved in the rocks on the Earth, and then sort of analyzing them and understanding how the rocks form and deform, we can say something about plate tectonics, the way that tectonic plates move around their surface, and we can understand how earthquakes work as well. And we can use the rocks that are recording all of these things to look way back into Earth's history and understand things about how past earthquakes happened as well. Okay. We also have a number of groups actually studying volcanoes, research related to volcanoes and igneous rocks. These are the rocks that cool from melted rocks. So maybe they'll cool beneath the ground, or they'll erupt onto the surface in volcanoes and cool on the outside. And so Professor Kim Berlow is one of the professors in our department working on this, and she looks at both sort of igneous petrology, the study of the rocks, and also the gases that are produced from volcanoes. We also have, this is a very broad discipline, but we also have scientists studying minerals and crystals. These are sort of the building blocks of rocks that then form the Earth. And economic geology, so how do we find minerals and what can we use them for in our society? So this is Jeanne Paquette, who's also one of the most senior professors in our department, most senior women in our department, and an excellent teacher. And this is just a PhD student in another group, Rowan Wellenberg, who is an economic geologist. So working in the field and working in the lab, we can look at minerals and understand how they form, what are their structures like, and from that we can understand what the properties are. Okay, and second last but not least, we have actually our newest member of the department who will be joining us this summer, Professor Nagisa Mumudi. She is a geobiologist and actually a microgeobiologist. So she looks at marine sediments. She tries to understand sort of life in marine sediments and microbes, which are very, very tiny organisms in marine sediments, and understanding how they release CO2, which of course is critical for the climate, and then in turn how climate change in the future is going to sort of affect these processes of producing CO2 from microbes. And we also have a number of groups working on topics related to climate change, and in particular ice and water. So myself, and I'll tell you much more about my research in a minute. But we also have geochemistry. So we have students and professors going out in ships in the Arctic to try to understand the geochemistry of the ocean there, and it's sort of changing in response to climate change. This is a graduate student in the cryohydrogeology, so hydrology meets geology meets cryology, which is sort of the study of the ice. So this group works on glaciers and sort of land water, groundwater in the Earth system. Okay, so that is sort of an overview of, a very broad overview of the types of problems that we work on. And of course, we also have people working on other planets, exoplanets and things. But it's quite a diverse department, and we have a lot of women in the faculty, which is, I think, quite good for an earth sciences department. So this is my group. So I work on climate change, and I work on sort of geophysics, ice dynamics. How do ice sheets evolve in response to climate change, both in the past and in the present and in the future? And how do oceans change in response? How do water levels change? And I also think about how the planet as a whole deforms and rotates and responds to sort of moving masses of ice and water around its surface. So I told my students, actually, these are, I think, the only pictures of men that you're going to see, but they're my group, so I had to put them up there. But all the rest, I think, is women. But so this is my group. I have a good group of sort of postdocs and a couple of PhD students and a master's student and a number of undergrads who come and go from different disciplines. So that's really great. We get undergraduate students coming in from different backgrounds and getting a taste of what research is like during the summers. And so to sort of how do we do our science, I mentioned there's a lot of different ways to go about studying the Earth. So what does my work look like? What do I actually do? Well, so we go to glaciers. This is the picture of the Jakobshavn Glacier in Greenland. It's one of the fastest flowing glaciers in the world. So it sort of sieves ice, it sends ice out into the ocean from the Greenland ice sheet. And so this is actually taken from a conference that we had. They took, which brings me to my next picture, so I mainly work with computers. I build computer models, mathematical models, and physical models, physics, using math and physics. I build models of how ice sheets and the Earth and water work. And so much of my work is done on a really big supercomputer. So this is what a supercomputer or a big computer cluster looks like. And this is located somewhere in downtown Montreal. And then we work on our computers and we try to understand the physics of these systems. And so this was actually taken from a conference that they had in Greenland in this area so that people who work on ice sheets at their computers can actually go and see this. And this was a while ago. This was a number of years ago. And now, actually, I'm going back to this same location to do field work this summer. So I've managed to come full circle and included some field work in that as well. So there are a lot of travel for conferences. Another great thing about my job is that I work with collaborators from all over the world. So this is a training school in Norway that sort of an interdisciplinary look at climate change, running courses for graduate students and postdocs. And so I've attended, and I'm going this fall to actually go and be an instructor at one of these. And when I'm in Montreal, the benefit of using a computer a lot is that actually, when I don't need to be in my office, I can take my computer and explore Montreal's coffee shops. So this is one of my favorites. It's a cat cafe, and this is actually myself working with another professor of statistics in the background. So I get to work from many different places and interact with people around the world in my job. Okay, so that's how we go about it. And now I'm going to give you a taste of my research, what the kinds of things that my group thinks about. So to start, this is a map from NASA, an image of the lights on the Earth at night. And so what you see, so the black areas are ocean, and what you can see from looking at this picture is that most of the world's population lives near the coastlines, okay? So in fact, 80% of the world's population lives within 60 kilometers of the coast. And so if we think about vertical height, actually 380 million people live within 10 meters of vertical height of the coastlines. And most of the world's sort of megacities, or areas where populations are concentrated, are right on the coastline, right? Coastal cities is where we want to build. And so thinking about sea level change, it's sort of there's a real human impact there. And so it's very important for us to know how much and how fast is sea level going to change in the future in response to ongoing climate changes. So we know that the climate is changing right now. If we continue to emit greenhouse gases and CO2, the climate will continue to warm, and the warming will accelerate. And with it, the sea levels will rise, so the volume of the ocean will increase. And one of the major contributors to sea level change now, and especially going to sort of be the dominant contributor in the future, is the effect of warming our ice sheets and then leading to melting ice that goes into the ocean and changes the water levels. So we have two ice sheets on the Earth today. We have the Greenland ice sheet in the Arctic. So if we melted the whole thing and we spread the water over the surface of the oceans evenly, water levels would go up by 7 meters. And in the Antarctic, we don't often flip the world over and look at its pole, but the Antarctic ice sheet is very big. And if you melted the whole thing, you would raise sea level by 57 meters if you spread the water evenly. And there's actually a section, the western section of the ice sheet, the West Antarctic ice sheet, that's sort of shown signs that it's collapsed in the future in response to climate changes. And so we're particularly concerned about that being prone to rapid retreat in the future. So just to give you an idea of how ice sheets work, this is a simulation showing observations from GRACE satellites. These are satellites that orbit the Earth. They're a pair of satellites, and they measure the mass below them. And so we've been measuring, the satellites have been around since 2002. They just finished, I think this year, they finally ended their journey, and there'll be GRACE 2 coming up soon. But this is a simulation from those measurements, or this is a sort of a plot from those measurements showing mass loss from the Greenland ice sheet. So you can see along here there are these ice streams. So these lines that are flowing out are showing the flow of ice. So ice sheets sort of, you can picture accumulate mass through snowfall from above, like a pile of honey, and then they flow outwards under their own weight, and they are sort of channeled into these ice streams. So this is the Jakobshavn area that I mentioned earlier. And I'll just play that one more time. So the red areas are showing increased ice loss. This is the amount of ice that is being lost. And here you're showing the sum of all of the average mass loss. So you can see it going up in winter and down in summer as the seasons happen. But the overall trend is down, right? So the Greenland ice sheet is losing mass. It's losing more mass each summer than it's gaining in winter. And so the overall mass trend is down. Okay, so that's Greenland, and it's very dependent on the sort of climate around. The Antarctic is thought to be potentially prone to sort of a rapid unstable retreat. So what that means is that it might reach a critical stage in some areas where if you retreat beyond a certain point, the retreat will continue regardless of what you do with the climate. And it has to do with that it's sitting on bedrock that lies below the sea surface height. So it interacts with the water around it. And so this is for scale. This is just the Antarctic overlain on North America. So this is, right, it's a big ice sheet. It's a continental scale ice sheet. So, up to about 4 kilometers thick in some places in the eastern section. So it's a lot of ice. And there has been a lot of work sort of suggesting that this is one of the ice sheets that we're most concerned about in the near-term future for sea level change. It could retreat, and it's very challenging to model because it evolves on so many different sort of timescales, from really short calving off, breaking off of icebergs that happen on, down to hours timescales, to sort of these big cycles of change over, tens of thousands of years. So challenging to model from that perspective. Also, getting there and working there and collecting data is quite a challenge. So one would need to fly. You can only fly ever so often because the weather is so severe. And it's really big, so it's difficult to get a broad idea of what's going on. But there's been a really big increase in the amount of information and data that we've been able to collect as sort of technologies improve and instruments improve, and we get better at going there and knowing information and having instruments survive the winter. And actually tying this back to women in science, there is a really interesting history of women in Antarctica. So this is Ingrid Christensen, who is the first woman on record to have viewed the Antarctic. And she was a Norwegian polar explorer. But actually, women weren't allowed to do science, weren't allowed to go to Antarctica until 1956. It was when the first woman was able to go to Antarctica to do science. And since then, there has been a rapid increase in the number of women who are doing science there and the way that the sort of research community is treating them. So this is zooming forward to today. This is actually if you remember the Women's March from last year, they had a Women's March in Antarctica. So this is a boat along the Arctic Peninsula where they had a Women's March out there. And recently, in 2016, there was an effort there's been a lot of work done by women that's important and contributed a lot to our understanding of the ice sheet, but it wasn't recognized. It hasn't, if you went in 2015 and tried to find women who have worked in Antarctica, you wouldn't find very many pictures, you wouldn't find very many profiles. And so there was a group of women who decided, okay, we need to fix that, and they did what's called a wikibomb, the Women of Antarctica wikibomb. So they reached out to the whole community and said, tell us who are the women who have done important work, what have they done, provide us with references, we're going to make Wikipedia pages for them all. And it's not actually insignificant to make a Wikipedia page. If you put a page up and they aren't deemed important enough, they'll just be gone the next day. So you really have to show your references. And so they, through this sort of community outreach and a lot of work by a few as well, they were, and in conjunction with Women in Red, who is a Wikipedia organization who sort of does this sort of thing for different communities, they were able to add over 100 bios and I think 75 profile pictures of women doing research, so that the next generation can look and find pictures of women doing the kind of work that they want to do. And I'll make this point again at the end, but representation is really important. So I was actually, this was the first time it was I was at an Antarctic research conference, and they had the launch of this, and I was at this conference for the first time, and it just really had it made me feel like I could be me and be here. And so it's really important. Okay, so that was aside to Antarctic. I encourage you to all look up more information about women contributing to Antarctic research. But okay, so we have ice sheets. They're prone to retreating in a warming climate and contributing to sea level change. What happens when you melt an ice sheet? So one would think we melt ice, we put water in the oceans, water levels go up everywhere, right? It's sort of the bathtub model of sea level change. And of course, as you can guess, that's actually not at all the way that the world works. So this is a prediction of the pattern of sea level change you would see if you melted from the Greenland ice sheet up here and the West Antarctic ice sheet down here. And so you can see the pattern is very variable. There is a greater, so this is sort of normalized by the average. So, a value of sort of 1.3 along here, along the North American east coast, if you melted from West Antarctic. That means that if you melted enough ice to raise sea level by 1 meter, if you spread it evenly, that area would see 1.3 meters of sea level change. If you melted enough to raise sea level by 5 meters, that area would see 6.5 meters of sea level change. So it's sort of a pattern that you can scale. And so we see a greater than average sea level rise far away from the ice sheet that you're melting. And then this area in blue, you actually see a sea level fall. you're melting an ice sheet here, and you're putting water in the oceans, and water levels are dropping at your feet. And the drop is actually quite big. So this is just the same field projected, turning the Earth on its pole. And you can see it goes down to -10. So that means if water was going up by a meter here, it would be going down by 10 meters in the Antarctic. So this is sort of a surprising effect. And there are two different sort of mechanisms that create this pattern. The first is the effect of gravity. So ice sheets have mass. They exert a gravitational attraction on the water around it. And so if you melt the ice sheet and you reduce its mass, that's going to reduce the attraction on the water around it. And water kind of goes where gravity tells it to. So you're reducing the gravitational field close to the ice sheet, which means that the sea surface falls as you retreat a melting ice sheet. Okay, and another thing happens, so you can see that it's not even moving away from the ice sheet either. There's sort of a spatial variability across the area far away from the oceans. And this is actually the effect on Earth rotation. So if you have a spinning ball that is the Earth, and then you take ice off of one side, then you can picture that the rotation axis is going to move towards that missing mass. And that if you shift the rotation axis of the spinning ball and it has water on it, it's going to change the water levels. So part of that sort of variability you see in the far field is that we're moving the Earth's rotation axis as we melt the ice sheet. And finally, there's a connection to the solid Earth that the ice sits on and that the oceans sit on as well. So when you remove a mass of ice from the land actually pops up under that ice sheet. And this sort of deformation that happens is called viscoelastic. So what is viscoelastic? Viscoelastic is kind of like a memory foam hybrid with springs mattress, right? I have one of these at home. So you get off of it, and there's an elastic effect, right? It rebounds elastically right away. And then there's the handprint that takes much longer, this sort of viscous flow back to even. And so the Earth does this as well. So this has this elastic effect. This is what happens right away. You melt ice, boom, this happens. But actually, this sort of viscous flow back to even takes place over thousands of years. So what that means is the Earth has a memory now of how we moved ice and water around it in the past. So there were big ice sheets in the past that don't exist today. And in particular, North America was 21,000 years ago, at the last glacial maximum, was covered by kilometers of ice, right? So this is my favorite XKCD comic. This is the skylines, and then the blue line shows the actual height of ice above these areas, right? So we in Montreal would have been sitting under 3.3 kilometers of ice. So much above our city skyline. And of course, it gets a little, less thick as you move towards the south. Okay, so that ice melted and retreated across the continent, and that retreat ended about 6,000 years ago. So the continent was ice-free 6,000 years ago. But if we look at the land in this area now, the land is actually still popping up from being covered with ice up until 6,000 years ago. And so this shows the rate of uplift. So in the center of Hudson Bay, that white area over there is popping up by over 1 centimeter a year. So that means the land is popping up and the sea levels are actually falling. And we can see these beach lines if we look in these areas of where water levels used to be as the land emerged from the water. Okay, so that was sort of a taste of the kinds of problems that I work on. I think about the past, and I think about the present and future, and how ice and water and the solid Earth all interact. And before we sort of wrap up that section, I wanted to talk about climate. So I think climate change is very connected to the issue of diversity. So climate change, we have climate change science and mitigation, and we think about the science and technology that's around that. But actually, climate change is also a global human rights issue. So And this is a quote that I took from an article that I really like that went out in 2015 that's called "Diversity in STEM Fields is Key to Stopping Climate Change." So the idea is that there's sort of a diverse and global population that is going to be impacted by climate change. And in order to do our best at being able to mitigate this, we, the people who are working on this problem, need to represent the same diversity as the people that we're trying to help. So STEM research and continuing to have diversity is really important in climate change research in particular. Okay. So before I move on, this is, I know some of you are students and sort of wondering what do professors actually do when they're not doing research and teaching. Well, we teach, which is a major component of our work. So I teach a number of different classes now, from sort of more advanced graduate level courses on geodynamics, the way that the earth and ice and water are moving, to understanding planet Earth, which is a big 200-person undergraduate general education class. And I really enjoy both of those types of teaching. We mentor and advise graduate students and postdoctoral fellows and even undergraduates in research. We give talks and seminars. We travel around the world to do that often. And we attend conferences to sort of present our research to our research communities and see what the research communities in other parts of the world are working on. We write proposals to get funding for our research. We review other scientists' work through reviewing papers and editorial work, that kind of thing. We do outreach activities like this talk, for example. Ways of communicating our science to the greater population. And there's some organizational work and some committee work and things that happen at the local university and also in the broader community. So an example of that, we had a conference that happens every 4 years. It's a big conference on sea level, an international conference on sea level. And so I was, last summer I was sort of on the organizational end of that, developing a program of speakers, and so we all converged on New York City at Columbia University, and to talk both about climate change and sea level science, but also about mitigation efforts and sort of coastal communities and things. Okay, and more. I'm sure there's something that I do that I didn't list here. We'll see what it is. Okay, so that's sort of my rough job description. It's a lot of different things. And I wanted to wrap up by giving a little bit more about me and how I got here. So I started with a degree in physics, an undergraduate degree in physics at the University of Toronto. And there the program was mostly men, and there were a few women, and we stuck together. So I'm left-handed, and there were, I think, 2 other people who were left-handed, and so we ended up sitting in the same, anyway. So we met each other, and we really stuck together and worked together on problem sets and things, and so that community really added some belonging that might have been lacking had I not had that community of women in amongst a larger group of men. So sort of finding a peer group is really helpful. So as I sort of wrapped up my physics degree, I think at the end of my 3rd year, I wasn't sure physics was for me, and I was thinking of doing just a major and finding something else to do. And I took a course called Physics of the Earth, and it was a really great course, and it was taught by who then became my PhD advisor a few years later. And so the other thing that I had that I was lucky to have was a really great mentor who supported me and gave me a lot of opportunities, and was a great teacher as well, so was able to sort of inspire my interest in this area. Okay. His name is Jerry Mitrovica. I wanted to put a picture of him, but well, sticking to just the women. Okay, so, and another thing so I finished that, and I had some research experience working with him in the summer, and then I took a break for a couple of years, and But I kept in touch with him, and he sort of said, oh, you should come back and do a PhD with me. Oh, okay, fine, how about a master's? So I came back with the intention of starting a 1-year master's, and I worked with him on a problem that was looking at this sea level pattern associated with melting the West Antarctic ice sheet that I showed you about. And it came out in a paper, a science paper, and as you can imagine, there was a lot of press attached to this. And I had thought about climate change and I thought about physics a lot, but I hadn't really connected just how societally relevant this kind of work is. And so through sort of interacting with the media and seeing the interest in this work, that really inspired me as well to keep going in it. So by the time I was sort of a couple of months into my master's, I was going to continue on to do a PhD. And then my advisor said, well, actually, I'm moving to Harvard. You should come. And so I applied to Harvard, and I continued on working with him to do a PhD at Harvard. And then the Department of Earth and Planetary Sciences, reached out, and a professor there said, I know you haven't finished your PhD, but we have this job opening, and you should probably apply. And so I applied, and I came here, and I just sort of thought, what an amazing department in an amazing university and an amazing city, and of course I want to be here. And so it was the first and last. I'm very lucky in that it was the first and last faculty job that I applied for. So that's sort of unusual. So to sort of add to that, there's a lot of hard work that takes to get through this list. And it also takes, good timing and a little bit of luck and doing the right things with the opportunities that come. So if you see an opportunity and you think maybe this could be good, I would encourage you to go for it and sort of be ready for it. Okay, and now I'm just going to wrap up with, so this was a talk about, earth science and climate science and women. And so I'm going to share sort of 4 thoughts, resources, advice, words I want more of the world to sort of know about. And this is more just related to me as a human in the world as opposed to specifically science, but of course it applies there. Okay, so advice and words number 1 is that representation really matters. I think it's useful for everybody to know this. So if you aren't seeing, if you're looking up at your future and you're not seeing what you want to do represented, you're not seeing you in the people that you're looking to, know that, that's a tougher situation for you. And look hard for somebody that you can, a mentor or somebody that you can relate to in a position you want to be. So these are the women of NASA, Lego toys, and this is actually my partner found an Arctic Lego station, and then he added a coffee cup and a chocolate bar. So this is me being represented in Legos, the most exciting thing. Okay, so representation matters, and being able to see people like you who are where you want to go is really helpful. So let's try to make that happen more in the future. The other thing that I try to sort of live by and I hope that other people live by as well, is an issue related to sort of making space for others and taking space yourself. So I feel that it's the job of the people in the room or the people in the space with the most privilege to make space for the people who have less privilege than them. So I recommend sort of recognizing your own power and position in a space and trying to advocate and include the people who have less power than you. So some classic examples would be men advocating for women, women advocating for non-binary people, white people advocating for people of color. So be aware of your own power and use it to make space for others. Okay, this is a slide inspired by a podcast that I really like called The Guilty Feminist. And so the advice is be yourself, which goes to representation as well, and demand a bigger piece of cake. So I think it's fair to say that the experiences and sort of expectations that we have of people who present as boys versus girls in our current society is different. So maybe it will be less different in the future, but for now, for most people, it's very different. And so the advice that this podcast gives, that I try to do, and it's sort of not always easy, is walk into a space expecting to be able to be yourself and be heard and be included and be treated equally despite your experience. So you will have had experience in the past that tells you that this isn't going to work. And so my advice to you is to try to ignore, when you can, that past experience and just keep walking in and demanding a bigger piece of cake. And this is difficult is also a really important message to know. So your instincts will work against you. You may even exclude yourself. I sometimes do that. And your expectations will not always be met. So you might continually walk in and expect, demand this, and they might say no. But I think keeping on trying is important. And so, and remembering that it's a journey, not a destination. So it's sort of an intention to try to continue, and you're not necessarily going to achieve it right away or perfectly. Okay, and the final piece of advice is to find your peers and mentors and support each other. So peer network groups have really helped me. These are a number of the graduate students and people I encountered through graduate school who are actually most of the people, the women on this slide are now also assistant faculty, assistant professors in other departments, and some have continued on to professional careers. But they've all helped me in times and added belonging to my life. And so if you're looking for a place to start, where do I want to go into earth sciences and where do I start? There is an Earth Science Women's Network, and it's really big, and they have a really great website. And so you can join the Earth Sciences Women's Network, and they have anywhere from undergraduates to tenured faculty members. And they have a wealth of information, and there's a forum where you can ask questions. So I encourage you to go and check this out if you're at all interested, and join if you're interested in this field. Okay, so that is the end. Thank you very much. What would an Antarctic presentation be without Henry?
We do have time for questions.
Oh, yes, we do. And your timetable is met to the moment. It's amazing.
Is this exactly what I'm...
Who would like questions? I think the young people here are going to take the microphone to anybody who wants to ask a question.
Hello.
Hi.
You analyzed the melting of the Antarctic ice sheet, and then you also analyzed the melting of the Greenland ice sheet. Mm-hmm. But I imagine both of them are happening at the same time. You're not one or the other. And has anybody taken a look at the effects of what one is doing to the other, as both are, like the interdependence of both? Because it almost looks like from the drawings you were showing, they're going to cancel out.
Aha, so yes, me, and a number of other people. So one thing to notice about that pattern, this might take a while to go back, but the sea level change you see at, here we go. So the sea level change, the rise that you see from Greenland melting is about a tenth of what would happen if a tenth of the signal or more or less to what would happen if you melted the Antarctic ice sheet. So locally, the sea level fall associated with that ice sheet melting sort of outweighs the rise that you see from other parts of the world. But in the past, we've had these really big ice sheets covering North America, and that's contributed sort of the volume of ice that was lost from 20,000 years ago to now is much greater in the northern hemisphere than the southern hemisphere. So in the past, there's actually a chance to look at those kinds of interactions, and it's something that I'm actively working on now. Yeah.
Hi, that was really interesting. Thank you. I guess I have a couple of questions. First question is, what is the ratio of men and women who are working in climate science? Do you have a ballpark there?
Oh, so climate science is a very
Broad?
broad term, and so I would think
Let's say climate change then. Climate change. Then.
climate change.
Yeah.
Well, yeah, that's it's also sort of fairly broad. So I think that if you look at the broad field, the ratio is quite good. If you look at the specific fields, I think there's still many fewer women in fields like physics and geophysics looking at climate change, or math and physics, that kind of thing. And in some of the other fields, the ratio might be going the other way. But I don't have a specific number for you.
Okay, so my actual question is this. Is there a disparity, or are male experts in climate change favored disproportionately by the media in terms of being featured in news pieces or interviews? Because anecdotally, most of the experts that I see in the media tend to be men. And I'm just wondering whether that's just my personal experience or if that's actually a phenomenon that is a real thing.
Yeah, so I think that is to do with the numbers and maybe a bit of the other as well. So I'm not sort of an expert in the field of gender diversity, but from my experience, there tends to be a better ratio at the sort of graduate student level than there is at the untenured faculty level, and then there is at the tenured faculty level. So that's sort of true across many fields in STEM, I think. So the experts that you end up seeing in the media tend to be men because there are more of them there, but there may be other things going on as well. Yeah, but actually so when I was working on this master's project that got big news, I think it was the CBC radio did an interview with me, and I sort of said, well, don't you want to interview I'm a first year graduate student, don't you want to interview and they said, no, we want to hear a woman's voice on this. We don't want to. So there is some effort to change that ratio. Yeah. Any other questions?
When you said that Washington would be underwater for the Antarctic melting, was that based on the models that it's not evenly distributed or just uniformly distributed? And what would be the difference?
Yeah, so it's due to that the melting the water is not uniformly distributed. So it turns out there's actually a sort of bullseye on the US East Coast for that particular story. And some of the other effects tend to be that the US East Coast is going to be very strongly impacted by sea level. Some of the other factors that contribute to sea level are also higher there. So there's one. Oh.
Hi, thank you for your talk. Just maybe following up on what my friend said, I was wondering what your perspective is on, so just comparing, like we had a talk from the physics, and so one of the problems in physics is more the pipeline and just having less women going in it in general. So do you find that is a problem in climate or this field of research, or I'm from the field of biology, and the problem seems to be more later on, and people not going in at later stages or losing women later. So just wondering where you see some barriers for women in this field.
Yeah, so I think the earth science and climate science by association it tends to be drawing from a lot of other disciplines. So I didn't know anything about earth science until I was almost finished my undergraduate. And so I was in the physics pipeline and sort of experienced some of the things that you said. So I think it depends on the discipline that you come from, but I think a number of, if one were to compare a physics undergraduate program to our Earth and Planetary Sciences department, the undergraduate level numbers are pretty even, I think, for our department. Is that? Yeah, so the undergraduate numbers, and I think also the graduate students are pretty even as well. So, and then as you go up, it gets less women. So if we wait long enough and we can keep them in the field, then yeah.
I was wondering, what is the timescale on this change? Because does that mean that the sea level rises that we're encountering today are actually from ice that has melted a few years ago, or is that the ice that's melting now?
Aha. So yes to both, actually. So we have this pattern here is for what happens right after you melt. So gravity, moves water relatively instantaneously. And there's this elastic uplift of the Earth that happens relatively instantaneously, sort of days at most. And so this pattern that you see is for that. But then if you wait longer, the Earth is going to continue and this pattern would change. Yeah. But for the sort of century, if you're thinking about the next 100 years, this is roughly the pattern that you would see. So you would start to see the viscous effects come out for ice, hundreds of years or more in the past. Yeah.
Well, I think it's time to close properly and thank not only our speaker, but also our moderator. So.
I guess I should have the microphone. Geez, thank you, Natalya. Thank you for coming. Thank you for coming to McGill. Thank you for joining our department.
Thank you.
Yeah, you're a wonderful find for us. You should know that Natalya has many opportunities to go elsewhere, but she's staying. So.
To thank Olivia, who when I first contacted her to do this tonight, the first thing she said, well, I have to ask my students. I teach on Wednesday nights. I will talk to them and I'll get back to you if they would be agreeable to letting me do this. And, I don't know what arrangements you made with them. So thanks for doing that and being that's a very, very democratic way of adjusting to these demands of your job. And also, I watched you a long time, and one of the first times I ever saw you was you were sitting in a computer lab when we were first getting our desktops and first starting to organize and understand this monitor. And you were totally surrounded by men. You were sitting, I think it was the only monitor in the room, and they were all clustered around you, and you were just explaining that as though this was the most natural thing. Well, didn't you realize that you press this? And I think it was still code, maybe ASCII. It was way over in, down in the burrows of EPS. No, I was at the door, but it really struck me because in those